Okay, welcome to my lesson. We are going to cover our topic called photoelectric effect. So we are going to cover the whole of this topic, and therefore I welcome you to this lesson. You listen, you can ask a question, or you can comment. Welcome. So we need to understand what is photoelectric effect. Then we'll talk about Einstein's equation of photoelectric effect. Then we'll talk about the factors that affect photoelectric effect. Now, photoelectric effect is a phenomenon in which electrons are emitted from a metal surface when a radiation of sufficient energy is irradiated on the metal. Yes, that is a photoelectric effect. When a radiation of sufficient energy is irradiated on a metal surface, then the electrons will gain energy, and therefore when the energy is sufficient enough, these electrons will be dislodged from the metal surface. That's actually what we call photoelectric effect. Now, after photoelectric effect, then we need to look at what we call the Einstein's equation of photoelectric effect. Now, according to Einstein, an electron will gain energy. Then it will gain a minimum energy that is sufficient to make it get dislodged from a metal surface. Then this minimum energy is called work function. So this is the energy that an electron needs to be irradiated from a metal surface. Now, when it has been dislodged from the metal surface, it now moves. Then it possesses the type of energy called kinetic energy. Therefore, according to the Einstein, the total energy of a photon, according to the quantum theory, is the work function plus the kinetic energy. Now, energy of a photon is given by the Planck's constant times the frequency of the source of radiation, which is given by F. Then the work function is given by the Planck's constant times the minimum frequency. This minimum frequency is called the threshold frequency. Threshold frequency is the minimum frequency that is needed for an electron to be dislodged from a metal surface. Therefore, if we add this work function plus the kinetic energy of an electron, when the electron has gained energy, it will be now moving. Therefore, the mass of an electron multiplied by the velocity at which that electron is moving at. Now, this is the kinetic energy of an electron after it has been dislodged from a metal surface. This is the work function, and this is the energy of a photon. Now, from waves, we know that the velocity of any radiation is given by frequency times the wavelength of that radiation. Therefore, if we make F the subject of the formula, or we express F in terms of velocity and lambda, that's the wavelength of the radiation, then our frequency will be given by the velocity of the radiation divided by the wavelength. Now, this velocity, if we consider the velocity of any radiation in a vacuum, then we'll say that frequency is given by C over lambda. Now, considering that our frequency is minimum, and then we come to the relation between frequency and wavelength, then for our minimum frequency, we need maximum wavelength. Reason being, frequency and the wavelength are inversely proportional. Therefore, threshold frequency is actually given by the velocity of the radiation in a vacuum divided by the maximum wavelength. Now, let us consider maximum wavelength. The maximum wavelength is actually the wavelength of a radiation beyond which there will be no emission of electrons from a metal surface. Therefore, we can substitute this one in our equation, our former equation. And therefore, if we do that, then we will have the Einstein's equation of photoelectric effect taking the form energy of a photon is equals to, so we substitute where we have the threshold frequency with C over lambda naught, then plus a half mass of the electron times the velocity of those electrons squared. So this is the Einstein's equation of photoelectric effect. It as well takes this form here. The two forms of Einstein's equation of photoelectric effect. Now we need to look at examples. In calculation, how do we apply the Einstein's equation of photoelectric effect in our calculations? Now, let us look at the question. The question is on the board. I want to give you 1 minute to write the question. Now, you have written the question. Let us read the question. The minimum frequency of light that can cause photoelectric emission from potassium surface is 5.37 times 10 raised to power 14 Hertz. When a surface is irradiated using a certain source, photoelectrons are emitted at a speed of, with a speed of 7.9 times 10 raised to power 5 meters per second. Calculate the work function. Now, when you hear about minimum frequency means threshold frequency. It is our F subscript naught. So our F subscript naught is 5.37 times 10 raised to power 14 Hertz. When the surface is irradiated by a certain source or using a certain source, photoelectrons are emitted with a speed. That's our velocity of the electron is 7.9 times 10 raised to power 5 meters per second. Calculate the work function. Our work function will be given by the Planck's constant times the frequency minimum. Therefore, Planck's constant is 6.63 times 10 raised to power negative 34 joule second times our minimum frequency, which is 5.37 times 10 raised to power 14 Hertz. Now, if you compute this one, 6.63 times 10 raised to power negative 14 or negative 34 joule second times 5.37 times 10 raised to power 14 gives you 3.56 times 10 raised to power negative 19 joules. Remember, work function is work is measured in joules. Okay. Now, let us look at, this is our question number A. Let us look at question number B. The minimum kinetic energy of photoelectrons kinetic energy is given by a half mass of the electrons. We are talking about kinetic energy of the electrons times the mass of those electrons squared. Therefore, this is a half times 9.11 times 10 raised to power negative 31 kilograms multiplied by velocity, which we are given as 7.9 times 10 raised to power 5 meters per second. We are talking about energy, therefore our units will be in joules. Therefore, considering the last question, this is number B. Number C. The frequency of the source of irradiation. Frequency of the source of irradiation. From the total energy of a photon, HF being given by the work function plus the kinetic energy. Frequency F here represents the frequency from the source of irradiation. Therefore, we have this work function and we have the kinetic energy. Therefore, HF will be equals to the work function, which we found to be 3.56 times 10 raised to power negative 19 joules plus the kinetic energy 2.84 times 10 raised to power negative 19 joules divided by H. You divide by H both sides. Therefore, you get F is equal to 3.56 times 10 raised to power negative 19 joules plus 2.84 times 10 raised to power negative 19 joules divided by 6.63 times 10 raised to power negative 34 joule second. And if you compute this one, you will get 9.65 times 10 raised to power 14 hertz. The units for frequency is hertz. So this is the frequency from the source of irradiation. So that's an example that applies the Einstein's equation of photoelectric effect. Now you can go and look for more examples for your own practice. We have looked at Einstein's equation of photoelectric effect. Then next we want to look at the factors which affect the photoelectric effect. We have three factors which affect photoelectric effect, and that's what I want us to look at. Factors affecting photoelectric effect. We have three factors. Number one is the intensity of the radiation. Number two is the nature of the metal. And number three is the energy of the radiation. Now, you need to understand how each of these factors affect the photoelectric effect. The speed at which the photoelectrons are emitted. Photoelectrons are the electrons which are emitted as a result of radiation on the metals. Now, the number of photoelectrons emitted is directly proportional to the intensity of the radiation. Meaning what? If we have a more intense radiation, then we'll have more photoelectrons emitted. As the nature of the metal, or the type of the metal, each metal has what its own minimum frequency called the threshold frequency, and therefore the photoelectrons emitted here depends on the minimum frequency for each photoelectrons. Now, of each metal, at the energy of the radiation, here you need to understand that energy is directly proportional to the frequency F from the source. Therefore, if the frequency of the radiation is high, then the photoelectrons which are emitted will be more, and therefore the kinetic energy for those photoelectrons will also be high. That's how each of these factors affect photoelectric effect here. We need to understand the relation between this frequency and the kinetic energy. Now, I would like to start from the Einstein's equation of photoelectric effect. Now, Einstein's equation of photoelectric effect is given by energy of a photon is given by the work function plus the kinetic energy. Now, the work function, the energy is given by HF, and the work function is given by HF naught, then plus the kinetic energy here, which is given as a half mass of the electron times the velocity of that electron squared. Now, what I want us to look at is the relation between the kinetic energy and the energy and the frequency of the radiation. Now, how are they related? Number one, I said that the energy is directly proportional to the frequency here. And therefore, if we want to graph or draw a graph of kinetic energy against the frequency here, then we would have to express kinetic energy in terms of this frequency from the radiation, the source of the radiation. Now, leaving this one on one side, let us take the work function to the other side. So HF will be kinetic energy will be equals to HF minus HF naught. Now, from our mathematical knowledge, this equation is in the form of y is equals to mx plus c, where our y, which is the vertical axis, is represented by the kinetic energy. Our other variable here is x, which is frequency from the source of the radiation. And our vertical axis intercept is our work function, which is HF naught. And therefore, having said that, students, it means that our slope of that graph will be given by the Planck's constant. Therefore, this is a straight line graph. It takes this measure where the vertical axis is the kinetic energy in joules. Then the horizontal axis will take frequency, will be frequency in hertz. And our graph will be a straight line cutting the vertical intercept, the vertical axis, that is the kinetic energy axis, at a negative because of the negative here. We take this measure. And this means because C mathematically is the vertical axis intercept, and therefore our kinetic energy intercept will be represented by HF naught, which is the work function. And this work function will be in joules. So these are at a negative. Now, if we calculate the slope of this graph, that is, our vertical axis will be having change in kinetic energy, our horizontal axis will be change in frequency, therefore our slope will be change in kinetic energy over change in frequency, which will give us the Planck's constant. Now, lastly, we have a special intercept here. This special intercept is our threshold frequency, F subscript naught. Therefore, the horizontal intercept or the F intercept is our threshold frequency. So, I come to the end of this concept. If there's any question, may I know by commenting or asking a question or using any other means that is available. You can reach me out at any time. I am available. I will explain why you have not understood well.